loud. All right. So chapter number 7 is about the periodicity and the periodic table. So this chapter is actually easier. It all comes from several tables I'll show you later. Actually, let's just start on the questions. First one, going to use draw function over here. All right, it's asking the atomic radius generally increases as we move. Okay, this is a conceptual question and asking you in this periodic table that how the radius of the atoms change. So if we pull out the slides, 6, 7 over here, and then go to periodicity. Let me minimize this, move it up. All right, so periodicity, and then we go down. We first talked about effective nuclear charge, and then we talk about the size of atoms. So if you look at the periodic table over here, and then the size would change, it would increase as we go down a column, and it also increases as we go from left, that word doesn't exist, right? From right to left of that period, right? So this is a thing to pay attention to. It increases from right to left, not from left to right. So if you go back to the question here, atomic radius generally increases as we move down a group. This is correct. If we move down a group, that's correct. And from right to left across a period. So A here is the correct answer. That's number 1. Okay, now question number 2 is, of the following, which gives the correct order for atomic radius? Again, similar question. Atomic radius for these 4 elements. All right, and then we're going to use the same table again and to see where the elements are. So what elements do we have? Magnesium, sodium. I have to move them around so we can see them. Let me move this around a little bit. Okay, let's see where they are. We have magnesium. Magnesium is here. Sodium's here. What's the other 3? Phosphorus here. And then silicon here. And next one is the last one is argon, AR. Okay, now we see they're actually all in the same period. They're period 1, 2, they're all period 3 elements. And going from left to right, the size decreases, right? So the largest one would be sodium, and the smallest one would be argon, right? And let's see. Okay, the order would be, okay, they are arranging them from the largest to the smallest. So we have, which one would be the largest? Sodium would be the largest, and the answer would be D, right? And let's double check. Argon would be smallest, and then here for D, argon is the smallest here. So the answer is D. Let me double check, yes. D over here. So I can see the inconvenience of doing online test, as if you just have everything just on one screen, then you have to just move back and forth between different windows, and that's kind of difficult. So if you can have your book ready, if you have a hard copy, or if you have a printer where you can actually print all the tables for chapter 7, or have it on a handy device, and that would be really convenient. Now let's take a look at question number 3. Question number 3 here, which isoelectronic series below is correctly arranged in order of increasing radius. Now, the first two questions are all neutral atoms, and here we are going from neutral atoms to the size of ions. And we remember that, let's see over here. Let me pull back to the slides. When you go to size of ions, when you remove electrons, the size of the ion would decrease compared to the neutral atom. When you add electrons to form anion, so adding electrons to form anion, their size would increase. But in this question, the tricky part is that, actually this is what makes the question easier, is that they are isoelectronic series, meaning they have the same number of electrons. So I'm going to go back to this periodic table again and take a look at this. So what atoms do we have? We have potassium. Let me label them over here. So first we have potassium, that's K, potassium, but K plus. Then K plus would have the octet configuration as argon, right? And we also have calcium. Calcium is here right next to potassium. When it loses two, how many valence electrons does it have? It has two, right? Because it's a 2A element. So it has two valence electrons. And then it likes to lose that two electrons to have an octet structure, the same as argon. So that's potassium 1 plus and calcium 2 plus. Next one is argon. And the fourth element in this question is chloride ion. So chloride ion, when chloride likes to gain one electron to form chloride ion with the same electron configuration as argon again. So these are the isoelectric series that they have exactly the same number of electrons. Now, then what would determine their size in this case? And that would be determined by the concept here, the effective nucleus charge. So if the charge the electron in the outermost shell feel, if it feel a larger charge, what would happen? The attractive force will be larger, and therefore the size of the ion will be smaller, right? So we go from here to here and find out which one has the highest effective nuclear charge, and that one will have the smallest size. And which one would have the smallest charge, effective nuclear charge? That would be calcium over here. The one has the, wait a second, what did I say? Oh, the one has the highest effective nucleus charge will be calcium here, and which will have the smallest size, calcium 2 plus over here. And therefore, we are going to choose from C, D, and E. And let's see which one has the smallest nucleus charge, effective nuclear charge, and that would be chlorine. And therefore, chlorine would be the largest. So we choose between C and D. And then if we look at the order, actually, it should be calcium the smallest, and next one would be potassium ion. And the next would be argon, and the largest would be calcium chloride. Excuse me. The largest one would be chloride ion. Okay, so the answer would be D. If you have question about this, just speak up, unmute yourself, and then let me know. So isoelectric series, pretty much what you will need to count is just look at the how many protons there are in their nucleus, in their nuclei. Yes, this will be recorded and it will be posted later. So if you have questions, you're not sure about the isoelectric series, take a look at the slides. So what you're looking for is the one with the highest effective nucleus charge. And effective nucleus charge is defined by, let's go over here to the very beginning. It's defined by, let's clear this. It's defined by, I keep repeating this, sorry. This is an effective nuclear charge, whereas Z is the number of protons in the nucleus, and S is called a screening constant and is the number of inner electrons. And therefore, if you look at this few over here and see which one has the, and if you look at their relations over here of the effective nucleus charge, then what we see is that it increases going from left to right within the same, okay, here. Take a look at this line here. It increases going from left to period. And when you go to next period, they are actually similar and then go up again like this. So that is the, okay, we also reviewed effective nuclear charge here. Actually, okay, now let's go back. We're distracted too much. Okay, now let's go back to this question. So, okay, let me tell you this. When you are asked to determine the correct order of the atomic radius, just for not this question, this one, isoelectronic theories, just look at which one has the highest number of protons in their nuclei, and that one would be the smallest, and vice versa, right? Okay, now moving on to the next question. Question number 4 is, which of the following correctly represents the first ionization of oxygen? So ionization meaning to, it means to remove electrons from the atom or ion. So first ionization corresponds to removing one electron, and second ionization represents moving the second electron, and so on and so forth. And the third ionization would be removing the third electron. It doesn't mean moving 3 electrons, it means the energy it takes to remove the third electron. So let's take a look at which one represents removal of the first electron, which is the ionization energy in this. So oxygen in the gaseous state lose 1 electron here to form 1 positive charged ion, and this represents the first ionization energy. Okay, then I'm going to ask you which equation of this 4 represents the second ionization energy, or represent the second ionization of oxygen, to be more accurate. Second ionization of oxygen, which one would it be? It would be this one? No. Would be this one? No. None of them, actually. So the second ionization energy would be represented by starting from this one, starting from the first. So 1 electron has already been removed. Now we are going to remove the second one. So going from 1 plus to 2 plus, still in the gaseous state, plus 1 electron. So this represents the second ionization of oxygen. So which leads us to question number 5. Which of the following correctly represents the third ionization of aluminum? And then you can try to do this on your own and see which is the correct answer. I'm going to give you 30 seconds. I think it's enough to come up with an answer for this. Anyone has an answer? Yay, got one. Is it E? Is it E? Yes, the correct answer is E. So losing one electron, so this one, it already lost 2 electrons, therefore it carries 2 positive charges. Now it's going to lose its third electron to form aluminum 3+, and this represents the third ionization. Yes, and for the rest of like this, something like this, let's take a look at this one. This one over here. This one over here, it means it gained the electron to form an anion, and this is electron affinity. So these are two opposite things. Ionization represents losing electrons, and electron affinity meaning gaining electrons. So let's take a look at question number 6, which is about electron affinity. Now, of the following elements, you're given 5 different elements. Then which one has the most negative electron affinity? Most negative electron affinity. So when it gains electron, because the attractive force between the electron and the nucleus, therefore gaining electron usually releases energy, therefore it has a negative electron affinity. And the stronger this attractive force is, the more negative the electron affinity would be, right? And therefore, if you go to, this is the trend for first ionization energy, and this is the trend for electron affinity. And then when we looked at this, and we said that actually the the periodicity is not very clear for electron affinity, but there are a few things we need to pay attention to. And here I'm going to reduce it to only 2 things. One is the hydrogen groups. They have very negative electron affinity. And that's because that when they gain 1 electron, they're going to have an octet structure the same as the noble gas elements. Therefore, it releases a lot of energy to be in a very energetically stable state. Does it make sense? Because they have the electron configuration of this. So when it gains 1 electron, it's going to have an octet structure, which is very stable. Therefore, it releases a lot of energy. Therefore, they have the most negative electron affinity. And within this group, that the electron affinity is the most negative for fluorine. Therefore, fluorine is the most reactive nonmetal. Whenever it comes in contact with, it's going to remove the electron from the other atoms. So that is fluorine. And another one to know is that for the noble gas elements, their electron affinity is positive, so they don't attract any or gain any electrons. So going back to this question over here, now you are able to determine that which one has the most energy, which one has the most negative electron affinity, and given these elements. So if I look at this question, I will first rule out this, because these 2, sulfur and selenide, they are in the oxygen group, because we know these 3, which belong to the halogen group, will have the most negative electron affinity. And then we compare this 3, which would have the most electronegative one, most negative one, and then we know that it's good to know and memorize it, so you don't have to go to this table every time, which takes a lot of time. That if we compare this one, and this one, actually this one has the most chlorine, has the most negative electron affinity. So that is how to answer this question. All right, question number 7. Which of the following is not a characteristic of metals? Okay, this question is slightly different. Characteristic of metals and which is not a characteristic of metal. Acidic oxides. So does metal form acidic oxides or basic oxides? If we are going to have a metal oxide and put it in water, what will it form? It's going to form sodium hydroxide, which is a strong base. Therefore, metal oxides are basic, they are not acidic. Therefore, this is not a characteristic of metal, so the correct answer is A. So what would be acidic? That would be inorganic oxides like carbon dioxide. And when you put it in water, now we have carbonated water. Some of you probably like it very much. And it forms the acid. Okay, let's still take a look at B through D. So low ionization energies, yes, for metals. Yes, that's true because they compare to non-metals. Because they have low ionization energy, therefore, they tend to lose electrons to form cations, and those are metals. Malleability, definitely sure. Definitely sure. Ductility, yes. And when you think of non-metal in comparison, then you're thinking of all those like sulfur powders and oxygen gas, and they don't have any of these material properties, right? Okay, so that's question number 7. Question number 8. We're moving pretty fast. For a given many electron atom, the greatest effective nuclear charge experienced by an electron in a which subshell? Okay, then to answer this, we have to go back to the definition for effective nuclear charge. Effective nuclear charge is defined by, as we just reviewed, the actual charge for the nucleus minus as the screening constant, the number of inner core, the number of inner shell electrons or core electrons. And the reason is for, and the meaning for this the effective nuclear charge is that, so this is the nucleus. And then what I'm going to have, it's, for example, I'm just going to draw the s orbitals. S orbitals, S orbitals. So if you have, for example, this is 1s, this is 2s, and this is 3s, and if you have an electron that is moving here, in the meantime, you also have electrons moving in these inner shells, and the nucleus charge or the effective attractive force, this electron going to feel from this nucleus will be shielded by these electrons in the inner shells because of the repulsive forces between them, which kind of cancel out, right? So therefore, in this question is asking that for a given many electron atom, the greatest effective nuclear charge experienced by an electron in which subshell, so that if you look at this subshell, the 1s subshell, then it doesn't have any electrons inside of it. So there's no repulsive force. It feels all the attractive force that come from the nucleus without any shielding. However, if you look at number 2s here, then the force it feels from the nucleus will be shielded by this electron in the 1s orbital, and so on, so forth. Therefore, in this question, you just look for which one is the electron that is closest to the nucleus, and that would be the one that has the greatest effective nucleus charge, because the effective equals to, the effective equals to Z minus, what is the symbol again here? S, screening constant. So we use S as a symbol over here. So because they are, it's a given atom, so Z doesn't change, but S could change. When you have if it is in 6s, then you will have more electrons, inner shell electrons or core electrons. So S will increase and then this D effective decrease. But on the contrary, when you are in the 2s subshell, the S number would be very small, and therefore the D effective would be the largest. Therefore, the answer is C for this question. 8, number 8, question answer is C, correct? Yes. All right, question number 9. Sodium, we love sodium. And to be more precise, we love sodium chloride. Sodium reacts with element X. So we don't know what this element is, but it's okay, to form an ionic compound with the formula of this. And now calcium is going to react with X again to form, okay, so we are asked to identify the molecular formula. Now it's actually empirical formula to be more precise. So remember that when you have ionic compound, you can only write the empirical formula. Chapter 1 or 2? Yeah, doesn't matter. Okay, come back to this question. We know this formula, and we know that sodium carry 1 positive charge. And therefore, through this formula, we know that the charge on the X would be 3 minus, right? So that the overall charge would be 0. So then when you put calcium and X together, we know X carry 3 minus. And what about calcium? Alkali earth metal, group 2A, they tend to lose 2 electrons. Yes? Yes, 2 plus, great. Exactly. Therefore, now we can write B. Now we can write B. It's not responding. Okay, let's come back here. So we can just write, because this has 2 plus charges, X 3 minus charges. Remember how we did it? We put 3 here, we put 2 over here. So it's calcium 3, X 2. Correct answer is D. Don't pick C here. Sometimes it's tempting. 2, 3, C. No, definitely wrong answer. The correct answer is D. 9, D. Yes. All right. Question number. Okay. Question number. All right. So consider following electron configurations to answer the question 10 through 12. Hey guys, am I going too fast or too slow? Or it's okay? It's okay. Okay, good. Yeah, let me know if I'm going too fast or too slow. And then let's take a look at the next question. So we are given 5 different electron configurations. Actually, if you look at them, you're going to see that these are in row 3, right? These are row 3 elements. Okay, so first question, or question number 10 is, the electron configuration belonging to the atom with the highest second ionization energy is. So we are asked to find the highest second ionization energy. Not the first, but the second, and then the highest over here. So when you see this, like, this is confusing. How would I know which one would have the highest second ionization energy, right? When I see the highest ionization energy, especially for the second one, the first thing I would think about is removing core electrons. And the reason is that, so this is where we covered ionization energy. And if you go here using this table, we are going to see, okay, so I1, it's the first ionization energy. And if I compare first ionization to second ionization energy, second one is higher than the first. However, whenever we go from the valence electrons to the inner shell or the core electrons, there is a sharp, really sharp increase in that ionization energy. So to answer that question, the highest second ionization energy, so when the electron, second electron to be removed is it's an inner shell electron, it will have the highest ionization energy. So let's take a look at it to see if we have a case like this. Here, one, if we're going to remove one, then just remove the valence electron. However, if we're going to remove one more, then we have to remove one electron from this octet structure, which is very energetically very unfavorable. Therefore, it will have a very high second ionization energy. But if you compare the rest of it, they all have more than one electrons in the valence shell, so they don't have to remove the inner shell electron. So the answer here for this question is A. So highest second ionization energy, or it can also ask you highest third ionization energy, and the first thing you look for is the inner shell electrons. Now question 11, still using these 5 different atoms. The electron configuration that belongs to the atom with the lowest first ionization energy is, okay, first is highest, then now we are looking for the lowest first ionization energy, lowest first ionization energy, and then how to solve this question. Where do we find the lowest ionization energy? Lowest ionization energy would be the one that the attractive force between the nucleus and the electron is the smallest. So if we look at the trend over here, so let's take a look at this table here. If we go from the left to right, going from left to right, the ionization, the first ionization energy increases. And why is that? It's because that going from left to right, the effective is increasing, therefore the attractive force is increasing. However, if you look at this end, then the first ionization energy is especially low for these metals, but very high for these non-metals, right? So coming back to this question here, that which one would be easiest to remove? Which electron, the first electron would be the easiest to remove? I'm making this everything messy now. Okay, now it looks better. For 5 of this, think about it. Which electron would be the easiest to remove? Any answer here? Take a guess, or take a look at this table here. And I would say we got an answer here. 1. Yes, 1. And why is it 1? It's because 1 is on the left-hand side of this periodic table, right? Furthest to the left, exactly. Yeah, so when you're given these electron configurations, you can actually correlate them to the atoms in the periodic table. And another way to think about this is that for 1, actually the effective nucleus charge is the smallest because that D effective is equal to D minus S. And for all of them, S is the same because they're in the same period. So S correspond to all these electrons, so they're identical. However, going down here, the Z is increasing. So the number of protons, which equals to the number of electrons, is increasing. So the effective nucleus charge is increasing, and this attractive force is getting bigger, and it becomes more and more difficult to remove the first electron. Therefore, this one would be the lowest. So it's a simple question that you can figure out from the table. And then in the meantime, it also shows you that there are a lot of logic actually behind it, right? How you can correlate it to the periodic table. And you're also able to correlate this periodicity to their electron configurations, to the effective nucleus charge, right? Yeah, there are actually a lot of things in there. Okay, let me clear it. So it's both the highest and lowest? Yes and no. So we are talking about different kind of energy. We are talking about the lowest energy is the energy that's required to move the first electron. However, it has the highest energy to move the second electron. So yes, you're right. It's both the highest and lowest. But to be more accurate, that we are talking about different energies. First ionization energy versus second ionization energy. Yes, good, okay. Question number 12, still based on these 5 elements. The electron configuration of the atom with the most negative electron affinity is, okay, now we're talking about electron affinity. What did we say? Where do we find the most negative electron affinity? In the halogen group, right? Even if I don't go to, I'm not going to pull out the table again. Let's see and how you can solve this question from logical thinking. Most negative electron affinity, and I have to go to the furthest right to the periodic table. And the halogen group would have the highest electron affinity. And a halogen group has an electron configuration of Ns2, Np5. So it tends to get 1 more electron. And do we have anything like this here? Over here, right? To complete the octet. Exactly. There we go. So the correct answer here would be E for this question. 12. Of course, you can always, as it is an open book exam, you can always go to this one and see where do you have the most negative electron affinity, but you have to figure out what exactly that element is, right? Okay, question number 13. We're getting there. 2 more questions left for this chapter. All of the following noble gases have Ns2 and P6 valence electron configuration, except, this is easy. What do you think? There is only one exception, and that would be A, yes, helium. Hydrogen, helium, those are the 2 exceptions that they can only hold a maximum of 2 electrons because they only have the 1s atomic orbital. Cool. Answer is helium. So if I show you the periodic table, then helium is this one over here. And 2s2 for the rest of them, they all have Ns2 and Np6 valence electron configuration. All right, now last question. Clear, clear. Of the choices below, which gives the order for first ionization energies? Oh, ionization energy again. I'll let you try out this question and see if you can get it right. Let me pull up the, actually let me pull up this table here. So you can see it. Not this one. I have too many things open. Excuse me. You guys have to be a little bit patient with me. Okay, here we go. Make it smaller. I'm going to just move it here. Okay, here we go. Now I can see it. And which one gives the order for first ionization energy? I'm going to label it for you. We have chlorine. Where is chlorine? Chlorine is here. Sulfur, aluminum, argon, silicon. Okay, now it actually is easy because they're in the same period. And what would the order be from the largest to the smallest? What do you guys think? Let me see. I got the answer. No, I just mean to move it a little bit. I got the answer B. Everyone else? Agree?
Is it actually from largest to smallest, right?
Yeah, from largest to the smallest. So which would be the largest? If you just determine which one would be the largest, and then you can determine the answer, the correct answer. First ionization energy. Argon, yes. And therefore the correct answer is B, right? So you got it right. Because first of all, if you look at this, you have increasing ionization energy from left to right. So increases from left to right. So argon is the highest, and the next one would be chlorine. And that's enough for you to determine the correct answer, which is B, right? Yes. And argon, another way to look at this, if you look at all of them, and we said that for the noble gas elements, because they are so stable. So their first ionization energy is very high. Their electron affinity is also positive. And so by this information, you can determine that the answer would be B, right? Okay, so I'm going to stop the recording because we finished this chapter.